So today we're going to start talking about feeds and speeds. And I've been putting this video off for a while, trying to determine the best way to approach it. I want to give you the information, but I don't want to overwhelm you. I mean, this can get fairly complex. It can get into a lot of math if you choose to go that direction. We're going to purposefully avoid a lot of the math and instead use reference charts and programs and other methods of calculating that. Just to give you a quick view of an example, this is something I found through Google, and this is for drill speeds using high-speed steel, doing different types of materials, but a high-speed steel drill bit. You're also going to find that a lot of resellers and tool manufacturers will have sheets such as this that will help you calculate that information out, specific to their type. So this is for carbide end mills that are uncoated. Here are carbide end mills with an aluminum titanium nitride coating. And then you don't see these as often, but this was what was around, I guess, before computers were common. And this gives you, this one's made by a specific cutter manufacturer, and it's for specific tooling. So they've got high-speed steel with various coatings and solid carbide. There are elite series from this manufacturer, and there are different areas here where we can move this up and down. So we've got a slide rule basically to look at what's the recommended surface feet per minute, as well as our feed rate, so inches per tooth, depending on the end mill diameter. And then on this side, we can take some of that information and calculate out our spindle speeds and how quickly we're going to be removing stock and all that good stuff. So there are a few manufacturers that still make these, but not very many. A lot of this has been replaced by computer programs. So in here is one such program. This one I believe is called CNC Machinist Pro. There's a free version as well as a version that costs $5. And this has turning calculators on it, complete with cool little noises. So we can do cutoff and grooving, and we specify our starting and ending diameter, and again our SFM and our inches per revolution. And then we can do cut rate, I mean all this good stuff. Different conversions, those are just for turning. Here we have various milling, and then drilling. And then these will also have some references. So here we can choose a material. So let's go with, let's say, an M2 tool steel, and this will give us our turning SFM, our milling SFM, and our drilling SFM. And then it just has a few other things, like I said, some reference charts. So we've got decimal to fractional and metric conversion here in a reference chart style, and then the type of taps, both metric and imperial taps. So nice little handy chart inside your phone. There are information on center drill sizes. I mean, all kinds of little unique things. I don't know if this is the best one. This is just one I grabbed that gave some of the information and the availability. But there are also programs for the computer if you have a computer down in your shop, or a tablet, things along those lines. So let's begin by talking about why we care about speeds and feeds. We're really going to go over just a lot of general topics here in an introduction. Sorry about my chicken scratch, a little bit of a poor handwriting here. So one of the reasons that we care about this is just for our own general knowledge. Something that we may want to learn, something we may want to understand, and we don't really care all that much about it. Particularly as a hobbyist machinist, we're really going to be looking at this from a knowledge perspective, and to be able to have a better grasp of machining in general. Another reason we're going to look at this from a hobbyist perspective is for finish, our surface finish primarily. And some materials want to be cut at a higher speed, as I mentioned before, particularly aluminum. And that finish will only come at those higher speeds, but we don't want to go too high. Safety is another reason. Now, safety on some of the larger cutters and fly cutters can start to really throw chips at high speeds. On our smaller machines, not going to be as much of a concern, but it is something we still want to address. Now, tool life is one of the main reasons that we will also look at speeds and feeds, because if we run a particular tool through a particular material at too high of a speed, we can greatly reduce the lifespan of that tool, whether that be causing it to lose its heat treating or simply dulling the edge and requiring it to be resharpened. That's going to be a big concern. And one of the last reasons we're going to look at why is from an efficiency standpoint. And these bottom two are going to be the two main reasons for people in production environments or professionals, because they're concerned about maximizing their tool life, and they're also concerned about the number of parts per hour that they can produce. As hobbyists, if we take twice as long to produce a part, it's not going to affect our bottom line because we are just a hobbyist. We're not relying on the speed of machining for our income necessarily. So now, who does this information apply to? Primarily, the people who are going to be concerned with pushing feeds and speeds are professionals who are making money. Right? You want to optimize the use of your machines and the number of parts you can produce in a particular time. And so that's really where this is going to come into play, is from a professional standpoint. Now, the next group, I would say, are CNC hobbyists, because we start to get to the point where we can finally control our machine speeds and feeds and move the machine around at a faster rate than we may be able to do by hand, and a more consistent rate than we'd be able to do by hand. So if you're looking at CNC, you're going to be wanting to address the feeds and speeds quite a bit more, because you're taking some of the feel and the finesse out of it and putting this into a computer that's going to be calculating everything via straight raw math. And then last are the manual hobbyists, which is where we're at right now, at least where I'm at on my machines. I'm not running CNC in any of these videos yet, but we still do sometimes want to be able to push the speed that we can produce a part at a little bit faster. We can't always run slower, and slower is going to be safer. Slower isn't going to reduce tool life, but slower isn't going to be very efficient, and slower may not give us the best finish. So the manual hobbyists out there will also want to start to learn and address this type of information. One thing I want to kind of point out is that everything regarding feeds and speeds is a recommendation and a starting point. These aren't hard numbers. We're going to start to talk about some of the variables that go into the calculations here in a moment, and you're going to find that there will be wide speed ranges recommended, and that there are a lot of things that can affect what speed range is going to work best for you in your particular operation, on your particular machine, with your particular tooling, etc., etc., etc. So these are really just starting points and recommendations. You'll have to go up and down from here and really get a feel and observe what your machine is doing and how the part is coming out and things along those lines. So I mentioned that there are a lot of variables that go into this, and we're going to cover a lot of these in depth and in detail, but I wanted to give you an idea of the number of variables that can go into this, and some of these will be used to calculate others. Some of them are going to be fixed in our setups. Some of them are going to be variable on what we control. So let's start looking at some terms here and some acronyms. So surface feet per minute is one thing that you'll see quite frequently. If you're in the metric system, you'll usually see this as surface meters per minute or just meters per minute. Depending on how old the books are, some will just read this as feet per minute, and they will leave the S off. So there are various terms, and this is kind of one of the problems with speeds and feeds, is these terms aren't always hard set and universally used. So depth of cut is another variable that we'll have direct control over. And feed rate, and this is another area again where we start to get into some confusion, because sometimes surface feet per minute and feed rate are used interchangeably. So we'll go into each one of these again in detail if you don't understand what these are and what they mean and how they can affect your feeds and speed calculations. Some other terms we're going to talk about and determine how to calculate our revolutions per minute. On the Shoreline, we've got the advantage that we can dynamically change the revolutions per minute where we don't have fixed pulleys or gears that we have to manipulate. So we can rapidly change the RPM, which then goes into the SFM calculation. But we have the drawback of how do we measure the RPM. So we'll look at some options there. Now our cutter or our workpiece diameter is going to be another key component for us here. And these two primarily go into our surface feet per minute calculation. Our number of cutting points or teeth. When we're dealing on a lathe, we're dealing with single point tools, whereas on a mill, we can still use single point tools such as a fly cutter, but quite often we're going to be using end mills with commonly 2, 3, or 4 cutting teeth, or there are going to be some forming cutters that may have upwards of 12 or more cutting teeth on them. Our cutter material has to be taken into consideration. And our cutter material can be a variety of items. I've listed a few here. We can have a mild steel, which is typically known as high carbon steel or just carbon steel. These may be lower end or cheaper cutters that you get, or cutters that you're making yourself. High-speed steel, such as M2. Not all high-speed steel is equal. Some, again, lower quality high-speed steel tooling may not specify what they're made out of, and you're just playing a little bit of a guessing game there. Cobalt steel, such as M42. Carbide, which there are so many different variations on carbide and tungsten carbide that this can really come into play. But we can also generalize a lot of these things for our needs if we're not going for super specific. Then we also get into ceramic and diamond cutting materials if we're dealing with super alloys and things along those lines. Now our cutter geometry is also going to come into play. And our geometry here can include things such as roughing versus finish cutters, other various angles, which I've got helix, tip, rake, tip, radius, relief angle. There are so many different angles here. We're probably going to leave this to the manufacturers for the most part to give us recommendations. Now our cutter coatings are going to come into play as well. Are we using an uncoated tool, or are we using something with a black oxide or titanium nitride or zirconium nitride or titanium carbonitride or aluminum titanium nitride? There are so many various coatings out there, some of them proprietary and some of them standard, and this is going to affect our speeds and feeds to some extent as well. Some coatings will claim upwards of 800% production speed increase. Whether those are real numbers or sales numbers or something that you're going to have to determine on your own. Now, coolant or lubrication is going to be another factor for us. Are we using any sort of coolant, whether that simply be air cooling or forced air cooling or liquid cooling and various types of liquid or paste lubrication? Is it going to be flood? Is it going to be mist? Is it minimal? We've got so many different options there. Next, we have to start looking at our workpiece. What is it that we're attempting to cut? This is going to be another major factor for us in the workpiece material. Are we using cold rolled steel, hot rolled steel, aluminum, brass, titanium, super alloys, just Inconel and things along those lines? Are we dealing in plastics? Are we cutting wood? What are we doing there? So our workpiece material is going to have a very large impact. And then what is the operation we're doing? Depending on whether we're doing lathe turning, whether we're doing cutoff or knurling operations, face milling, end milling, slotting, drilling, these will all have different speed and feed recommendations that come into play. And then two of our limiting factors are going to be the rigidity of all of these components. The rigidity of our machine is definitely going to be one. The rigidity of our cutter, the rigidity of our workpiece is all going to come into play, because as we start to get into vibration, that vibration is going to significantly reduce tool life. It's going to lead to cutter breakage more often. It's going to lead to a poor surface finish, and we really want to avoid a lot of that vibration. And the rigidity is going to be a limiting factor for us there. There's only so much we can do on our smaller machines to help this. I mean, using proper work setups, using proper tool holding, things along those lines are going to help us, but we are going to be still fairly limited here. We're dealing with a machine that weighs, well under 50 pounds, is easy enough to carry from point to point. We're not dealing with a machine that weighs 1,500 pounds and has so much mass and thickness and rigidity. So we have to keep this in mind on our smaller machines. The other item we have to keep in mind in our smaller machines is power. If you take care of all these other items up here, power is going to really be your final limiting factor. If you've got the best cutter and the best setup and the most rigid with the best cooling and everything else optimized to where you can really push your setup, then your power is likely going to become your limitation. It's how fast can you spin a cutter while still keeping enough torque in order to power that cutter through the workpiece. So I don't want to scare you, but I do want you to understand that this isn't a simple topic and that there are a lot of variables that will go into this. Now, the reason that I'm going to be leaving a lot of the math out and the reason I'm going to be recommending the use of reference charts and computer programs and slide rules and things like that is to eliminate a lot of these decisions for us, so that we just punch the answer into a calculator and it will output what we need to do as far as changing our machine settings and our feed rates and our depths of cut, which are going to be really our three primary, are these first three. And again, some of these items go into these calculations up here, such as our RPM, our cutter workpiece diameter, our number of cutting points per teeth. We're going to talk about other terms such as inches per tooth, inches per minute, inches per revolution. And if you're dealing in the metric system, obviously a lot of these are going to be either millimeters or meters per. And what do these mean? And so we can really understand a lot of the charts and programs, because a lot of these terms are going to be on those programs as well. Now, a good reference is, I always recommend the Machinery's Handbook. In this 23rd edition, which was published 20, 30 years ago, there's still 50, 60 pages of information just on speeds and feeds in here. So if you want more information, if you want some of the math and the calculations, that will be in here. Wikipedia has got some other good references. If you don't have book references, or if you prefer to look things up online, there are a lot of good references and explanations of various things on speeds and feeds. Just be aware that it can add to your confusion, because again, some of these items over time have changed meaning slightly, particularly with the introduction of CNC. This has become a lot more important and critical. And so additional terms have been introduced, and others have been somewhat reused, and depending on what part of the world you're from, they may refer to something slightly different than another part of the world. And then, of course, the industry background. Are you mainly a computer geek dealing with CNC, or are you coming from a metal background? Are you coming from metal machining or metallurgy, cutter design, so on and so forth? There are always variations there. So I'm going to stop this video at this point to give you guys some time to think over all of the details that we've covered here. We've mostly introduced a lot of the variables and the terms and the hows and whys. We'll start to get into some of the actual nitty-gritty details in the next video on how we calculate these items and how it's going to affect our workpieces. Please leave in the comments anything else that you'd like to see. If you want to see the math, let me know. Otherwise, I'm going to skip over a lot of the mathematics. But if enough people say they want to see the math and see the geometry, then I'll go into more detail on those items. If you want to see the future videos in this series, please subscribe. And if you enjoy and appreciate these videos being produced, please give them a thumbs up. In future videos, initially I'm just going to be covering the calculation of these items, but later on as I get CNC up and running on my machine and start to introduce you guys to CNC, I'll augment the videos and we can show very, very specific variations on these items. So we can use the machine to spin at a very specific RPM with a very specific feed rate and see how that affects how long it takes to make a pass on a particular part, what type of vibration we get, and how it affects our surface finish, as well as both our workpiece and possibly our tooling temperatures, which will give us an indication of our tool life. So I do hope you have enjoyed this introduction to feeds and speeds, and I look forward to hearing from you.